Hey guys, Graves here. Let's take a look at review 16. Okay, so small block, mass 0.5 kilogram, placed on a point A, right? Friction, no friction, right? Zips down, zips around, comes there. Okay, so, right, 2 meters above, track is shown, release from rest, slides down negligible friction down track, allowing it to make the loop, right? Leaves the track at point C. Okay. Calculate the speed of the block when it leaves the track. Okay, so speed when it leaves the track. All right, so we are going to, hopefully you guys got when you did this, you're going to use energy, right? So what do I have at the top, right? What do I have? U. Okay, so that's right here, right? Conservation of energy, I have U. Then I'm looking when it gets over here. So what type of energy do I have here? Well, it looks like I still have U plus K. Okay, so what do I have? mgh plus 1/2 mv squared. All right, so it looks like I can do some slashing and burning. There goes my masses, right? Great. So what do I have? G, 10. How high up am I? 2, 10. How high up? 0.5 is equal to 1/2 v squared. Right, so 10, 5, 15, 30, square root of 30. So I did that already. It's about 5.5 meters per second. So that's how fast we are when I leave that guy right there, right? On the figure below, draw and label the forces, not components, that act on the block when it is at the top of the loop. All right, so let's do it on here. All right, so when I'm at the top of the loop, what do I have? Obviously, I have mg down. But what else do I have? Well, it's always in contact with the surface, right? Well, in this particular case it is, right? Because it makes the loop a loop, right? So what other force do I have? Well, I have to have Fn, which is a normal force, and that's down. Okay, so that's B. C, calculate the minimum speed the block can have at point B without losing contact with the track. Okay, so, by the way, we are going to use, right, this free body diagram for C. But there's something that's important about this, the minimum speed. So what is it about the minimum speed? Minimum speed, that is when the normal force is going to be equal to 0, right? Anything has to be 0, right? So I'm calculating, when I set the normal force equal to 0, right, I'm going to calculate from that point the minimum speed needed to make it around, okay? Minimum, right? Really, to make it, I need to be just a little bit above that, right? Okay, so let's look at how I handle that. So that really is going to be F net is equal to MA. So when I'm at that point there, what do I have? Fn, right? Fg. So it looks like Fn plus Fg is equal to what? MA. But in this special case, Fn is going to be equal to 0. So that goes away. So what do I have? Mg is equal to M. And it's going in a circle, so this is going to be what? V squared over R, right? By R. So that's an R, not 2R, right? So what do? Take this guy, bring it over here. So V is equal to what? GR square root, right? Because it was really V squared is equal to GR. Take the square root, right? Let's plug in from here. What do I have? Square root of 10 and 0.6. So it looks like it's the square root of 6, right? And I did that already. So 2.4 meters per second. So that's C. All right, D. What is D saying here? Calculate the minimum height, right, above the bottom of the track, which the block can still go around. So what's the minimum height needed to still make the loop? All right, so it looks like I have U is equal to what? U plus K. mgh plus 1/2 mv squared. Once again, masses go away. So 10, h is what I'm looking for, is equal to what? What did we say? This is 10. And we said that this was, Height. Okay, so let's take a look. What height do I have to make? So I have to actually make it this high over here, don't I? So the radius is 0.6. So I have to double that. So that's going to be 1.2 plus 1/2. And how fast did we say we were going here? 2.4, right? So 2.4 squared. Doing a little bit of math here, you get a height of 1.5 meters. So that's the height, right, that I need to, the minimum height that I need to make that loop the loop, I should say. Okay, so that is 16.1. Let's take a look at 16.2. Right? 16.2 is the ladybug problem. I think we did this one in class, but let's take a look at it again. Right? Good problem. Okay. Two ladybugs are standing on a rotating disc that is spinning clockwise, right? Counterclockwise, as shown in the figure. Assume friction in bearings of the axle is negligible. No friction there, right? Is the angular speed of A and B less than, greater than, or equal to? Well, what is angular speed? Angular speed is just describing, right, how my theta, right, is sweeping out per unit time, right? My angle, right, in radians is sweeping out per unit time. And what happens is, right, as this is spinning, right, if I had to do something like this, right, the angle that they sweep out is the same, right? So in this particular case, the angular speed is the same, okay? Why? Because they're both sweeping out the same angle in the same amount of time, okay? Linear speed. Okay, what about the linear speed compared to A and B? So the linear speed is A greater, and so what about the linear speed? Well, linear speed is going to be equal to, like V is going to be equal to what? There, right? Omega R. Okay? So from this equation here, right, my linear speed is omega R. Look, I'm farther away, right? So my linear speed has to be greater. Okay, justify your answer. You know, we can use something that looks like that. Okay, something from that equation there. Okay? All right, the ladybug begins to walk in a circular path in the direction of the disk's rotation. So the ladybug is going to walk on the outside like this, right? Oh, sorry, there you go, right? It's going to walk on the outside of the disk as it's turning. Okay? Does the magnitude of the angular momentum of the disk, not the ladybug, the system, increase, decrease, or stay the same? All right, so there's a couple of different ways to look at this. The way that I looked at it was, the way that I looked at this is, look, as the ladybug is walking, right, what is she doing? She's putting a force back on the table, right? So she walks this way, her force is on the table, or the disc, I should say, pushing the disc back that way. So, and that's the case, right, the disc should decrease. What's another way to look at it? Well, the momentum of the system consisting of the ladybug and the disc, the angular momentum, I should say, is always the same. It's always the same. But as the ladybug is walking in this direction, her angular momentum does what? Increases. So if the system consisting of the ladybug and the disc must be the same, if hers increases, what that means is the disc must decrease. Okay? So that's the answer to B. All right, different scenario, right? In a different scenario, a single ladybug is standing near the edge of the disc, point 0.9 R from the center, where R is the radius of the disc shown in below. The rotational inertia of the disc is I1, and the disc completes one rotation in 2.5 seconds. The ladybug then walks towards the center of the disc, the distance of 1.1 R from the center, and comes to a stop relative to the disc, as shown in figure 2. The rotation of the inertia is I2, and the disc completes one rotation every 2 seconds. Okay, so let's derive an equation for I2 in terms of I1. All right, let's see if I can fit that in over here. So L1 is equal to L2, right? Angular momentum, right? So I1 omega 1 is equal to I2 omega 2. Okay? All right, let's take a look at what omega is. Omega is my rotational speed. Okay? Now, another way to look at this is it's also my rotational frequency. look, I'm here, swip around, time is equal to 2.5 seconds. As I get closer, right, it does that time in what? 2 seconds. All right, so if this is also the angular frequency, so frequency is equal to 1 over the period, right? So I can write angular speed is also angular frequency, right? So what do I have? I1 is equal to 1 over I, so this is T1, right? T1 is going to be what? 2.5 is equal to I2, 1 over 2, right? So I1 is equal to 0.4, I2 is equal to 0.5, and I wanted I2 in terms of I1, so I'm going to divide by 0.5, I'm going to divide by 0.5, so 0.4 divided by 0.5, so I1 is let's just say 0.8 I1 is equal to I2, okay? And there are probably different ways you can express that as well, okay? So that is CI, all right? While the ladybug is walking towards the center of the disc, does it exert a torque on the disc? Well, the answer is, of course it does, right? Why is that? Because every time I take a step, right, the force of friction, it's moving this way, right? So it's moving this way. So which way does the force of friction act? The force of friction is back that way, right? Opposite motion, right? So the force of friction is this way, perpendicular to my rotation, so there has to be a torque. So the answer is yes, because there is a force, what? Perpendicular to motion. Okay? So here is 16, and have a good day.